When we ask a large language model to roleplay as a specific persona, we are implicitly treating it as a conditional probability estimator. For instance, asking a model to predict the opinions of a 30-year-old living in the US is a form of conditional inference. But if LLMs are truly acting as probability estimators, their outputs must obey the fundamental laws of mathematics. In this video, we will explore a groundbreaking paper that stress-tests LLMs against the basic axioms of probability, revealing a massive gap in how models represent aggregate versus fine-grained knowledge. To systematically test LLMs, the researchers constructed binary conditioning trees. The main takeaway here is that we can recursively partition a population into increasingly specific subgroups using binary attributes like age or employment status. According to the law of total probability, the overall population-level estimate must equal the prior weighted sum of these subpopulation estimates. By querying the LLM for both the subgroup priors and the conditional probabilities, we can mathematically reconstruct the aggregate population estimate at any level of the tree and compare it to the model's direct response. This methodology led to a shocking discovery called the macro fallacy. The key takeaway is that directly asking an LLM for a population-level estimate is systematically less accurate than asking it for fine-grained subpopulation estimates and manually aggregating them. As you can see in these charts, across different income thresholds and various state-of-the-art models, the mathematically reconstructed estimates consistently show a massive accuracy gain over direct prompting. The model possesses the correct subpopulation knowledge, but fails to naturally propagate it to the macro level. To understand why this happens, we must disentangle the two sources of error, the conditional estimates and the subgroup priors. The main takeaway is that as we refine the population into more specific subgroups, the conditional estimates become much more accurate because residual uncertainty is reduced. However, there is a trade-off. Estimating the exact population size or prior of highly specific subgroups becomes increasingly difficult for the model. This creates a concave curve where aggregation benefits peak at a moderate depth before declining due to noisy prior estimates. Can we help models overcome this limitation without manually querying every single subpopulation? The authors introduced a lightweight solution called micro-to-macro prompting. The core idea is to instruct the model to first explicitly reason about relevant subpopulations and their relative sizes within a single prompt before returning its final aggregate estimate. This simple intervention successfully recovers a significant portion of the aggregation benefit, proving that structuring the model's reasoning path can dramatically improve its statistical inference capabilities. To evaluate LLMs in scenarios where ground truth data is unavailable, the researchers designed two reference-free metrics, split consistency and order consistency. Split consistency measures whether a model's direct estimate for a group matches its aggregated estimate when that group is split into two. Order consistency checks if the model's estimate remains the same when the order of the conditioning attributes in the prompt is swapped. A mathematically coherent model must satisfy both of these properties, regardless of whether we have external data to verify the actual numbers. When evaluated across a wide range of frontier models, the results reveal widespread failures. The key takeaway is that statistical self-consistency does not automatically improve with general model capability. As shown in this comparison, even models with high scores on standard benchmarks show severe violations of both split and order consistency. This suggests that current post-training and alignment methods do not teach models to maintain a coherent internal system of probabilities, leaving statistical self-consistency as an unsaturated and crucial frontier for LLM evaluation. In conclusion, this research exposes a fundamental flaw in how modern LLMs handle probabilistic reasoning and persona prompting. While models contain rich, fine-grained subpopulation knowledge, they cannot reliably aggregate it on their own. By establishing statistical self-consistency as a reference-free evaluation framework, this paper provides a clear path forward. Future AI development must focus on explicitly enforcing these mathematical constraints during training, ensuring that the next generation of language models can reason about our world in a truly coherent and statistically sound manner.